Hi guys, back with part 2 of the lecture. My son's in the other room online gaming with his mates, so you might hear a bit of noise in the background. Sorry about that. Okay, so let's get into the lecture. So as I mentioned in the previous one, we're going to look at failure theories. So we both look at failure for ductile and brittle materials. So we predict failure using yield criteria, and we'll also look at some brittle failure criteria, and we'll introduce this yield criteria into design factors for strength-based design process. Now in this video, or in the lecture slides, there's a lot of slides that have a lot of just words. I'm not going to sit here and read them out to you. You can just read through those for yourself. Most of them are fairly self-evident. I might and easy to understand. I might pick out a few things here and there, but when you see a slide with lots of words on it, I'm probably just going to skip it and say, look, you guys can read that and understand it. Okay, so let's move on to the next bit. Okay, so here's a typical example. All right, so general considerations for the designer's responsibility in designing a machine part. Okay, so you can read through those for yourself. Right, so we need to take in lots of considerations for when we do design for strength. Right, so the basic thing that we'll be looking at here is defining a relationship between the applied stresses that we've calculated. So up till now we've calculated stresses using equations like stress equals my upon I for bending and shear stress equals TR upon J for torsion. And we need to compare those stresses with the strength of materials. So in the past, in mechanics of solids, for example, you might have calculated the stress due to bending, my upon I, and compared that directly with the yield stress or the ultimate tensile stress of the material. In most of those, if not all of those examples, they were simplified cases where you could just do that. And it wasn't explained to you that it was a simplified case, and you can't just always do that simple approach. So what we're going to do today is to look at more general failure criteria that you can apply in more general cases. Okay, so again, here's some more explanation and just information about different loads. Failure can mean lots of different things. So you might think of failure as breaking something broken into two pieces, but it can be more than that. It can be distorted, its reliability downgraded, or its function compromised in some way. So in this lecture we're going to focus on design for strength, but there's also design for stiffness. So you can have something that bends or deflects too much, but hasn't broken into two pieces, but it's still failed because it's failing to do the job that you've designed it for. Okay, so when we design for strength, we can design based on the yield strength, or we can design to the ultimate tensile strength of the material. And we'll look at what these are if you haven't come across these before. So understand that some of you would have done chemistry and material science here at uni. You may have done engineering studies at school, or you may have done neither of those. Okay, so we need to cater for students with all of those different backgrounds. So the goal of the design process is to achieve a suitable design factor or a factor of safety. Okay, and the strength of the material must of course be greater than the applied stresses. Okay, so we have two broad classes of materials. So those that we label as ductile materials that deform or stretch, change shape significantly before they fracture. So some typical examples of what you might think of as ductile materials are steel and aluminium. And then we also have brittle materials which yield or deform very little before they break into two pieces. Okay, and we'll have a look at some graphs in a second that show you that the yield strength in a brittle material is very close to the ultimate tensile strength. Okay. All right, so what we have here are two charts of stress versus strain, or you could think of it in terms of load versus deflection of a material. So we do standard tensile or compression tests. So these are results of tensile tests. So we might use a machine, something like this. This is simplified representation up here. So we would pull up on one or other of these blocks, or the crossheads as we call them. So here we have a base. Here the crosshead will move up or down, applying a tensile load to the specimen in here. And if we measure the load, divide by the cross-sectional area, we'll get stress. And if we measure the deflection and measure the change in deflection over the original length, we'll get the strain. Okay, so that's what we've plotted on this horizontal axis. So if we have a ductile material, we'll apply the load, it'll stretch, it'll get to this point here where we have the elastic limit. Okay, so here we have a linear elastic region, then we have the elastic limit, then we get to a yield point. So this is for steel, where you have this little drop off. For aluminium, this would just go up and continue to curve up like this. You don't have this little drop after the yield stress here. Okay, so here's the yield point, and then we continue to load. So it doesn't break into two pieces at the yield point. You can continue to load it. At this point we get to the ultimate tensile strength, and at this point we get what we call necking, and I'll show you a picture of that in a second. And then the load drops off when we're using engineering stress and strain. I'm not going to go into that now, that's in material science. Load drops off, and then we get to the final fracture point. Okay, in a brittle material, again we apply the load, we get deflection, convert that into stress and strain, have a linear initial region, get to maybe a yield point, maybe not, and very close after that we get to a final failure point. So after we go non-linear, usually the ultimate tensile strength and fracture is not very long after that. Okay, so that's a very brief introduction to material science. What I'll try and do for you is find a couple of good online YouTube videos, and you may have found these for yourself already anyway, but I'll find a couple that I think are good and put them into the more information below the video. Okay, so when we do these tests, so here we've got an indication of the type of failure that you get in ductile and brittle materials. So here's an aluminium. We get failure in shear. Okay, so we've got over here a picture showing a mild steel strip, which tends to be ductile, loaded in tension, and we see these what we call Luder's lines or slip lines at 45 degrees. And you may recall from Moore circle, and again we'll look at this again in a second, why these slip lines which are at 45 degrees are along the lines of maximum shear. Right, so here this is a typical failure of a ductile material in tension. So you can see these surfaces here. This is what we call a cup and cone failure. So these surfaces here are roughly at 45 degrees, and then you have this flat bit here, which is the final fracture surface. And in aluminium, this is very pronounced, depending on the relative ductility of the steel. You might get very little of this cup and cone, and you get more just this flat region where the final failure was in normal stress. But initially, the yielding begins at 45 degrees here along the planes of maximum shear. For a brittle material, the fracture surface will look like this, and brittle materials fail along planes of maximum normal stress. Okay, so here's some more words. I'm not going to read through those. They're pretty self-evident and easy to understand. Yep. Okay, so as I mentioned before, when you did something like this in mechanics of solids, or maybe even fundamentals of mechanical engineering, you may have calculated a stress and then just compared that directly with the yield stress or ultimate tensile stress of the material. That was okay then because you're looking at a simplified state of uniaxial state of stress. You may not have been told that at the time, but that's what you were doing. As you've seen in this subject, you can have biaxial or triaxial states of stress. So how do we work out if a triaxial state of stress? So you do your stress analysis, calculate the stress at a point, you get normal and shear stresses, you do your Moore circle to find the principal stresses and so on. How do you compare that state of stress to a single value of a yield stress, for example? So for ductile materials, the failure is usually specified by the initiation of yielding, and then for brittle materials, failure specified by fracture. Okay, so the theories of failure that we're going to look at for ductile materials, we'll look at the yield criteria, maximum shear stress theory, also known as Tresca criterion, and we also look at the maximum distortion energy theory, which is also known as the von Mises criterion. And then for fracture for brittle materials, we'll look at the maximum normal stress theory and also the Moore's failure criterion. So these have limited real practical value. They're good for very quick calculations, but if you're wanting to do serious design for brittle materials, you need to look at proper fracture mechanics, and we'll do that later in this subject. Okay, so firstly looking at the maximum shear stress theory, or the Tresca yield criterion. This says that a structural component is safe as long as the maximum shearing stress, now that could be the out of plane shear stress that we talked about in the first part of the lecture, where we looked at the absolute maximum shear stress out of plane. Okay, so given a complex or more than a uniaxial state of stress, we can do Moore circle and we can find the absolute maximum shear stress, and we can compare that with the yield stress divided by 2. Now, why do we divide by 2? Let's go over here. If we remember from Moore circle, right, if we plot our tensile stress state, so this is what we've got, uniaxial stress at the yield stress, this normal stress here is equal to the yield stress. Okay. At that point, the maximum shear stress is given by the top of the circle, right, as we've seen over the last week or two. And the value of this maximum shear stress is the radius of the circle, which is of course the yield stress divided by 2. Okay, and we can rotate our element to see that. Okay, so if we go back to here, right, if our absolute maximum shear stress is equal to the yield stress divided by 2, then we're predicting that yield occurs. Okay, and yield occurs by slipping on shear stress planes. Okay, right, and as I said before, right, in our tensile test, right, even though we've got uniaxial normal stress, doesn't mean that there's no shear stress in the material. It's just that it's at a different angle, right, or a different orientation than we're looking at here. Okay, so the yield criteria for plane stress. So again, I talked about how textbooks tend to try and simplify things and keep things in a 2D system, whereas I like to think of everything as 3D. So here they've recalled the rules where you have the normal stresses as found on Moore's circle. If they both have the same signs, then the yield criteria is that either of the two normal stresses have to be less than the yield stress. If the principal stresses have opposite signs, then we have a different equation. Okay, so stress 1 minus stress 2 has to be less than the yield stress. And at the boundaries, okay, so this is our criteria. If we're less than the yield stress, then we're safe. We haven't yielded yet. If we're at the boundary, so stress 1 is equal to the yield stress, when the principal stresses have the same signs, then we get yield. Okay, so this is the simplified case that you had in mech solids, for example. But in the case where we have biaxial stress, which is mostly the case, by the way, as you probably should recognize from doing your stress analysis problems, doing Moore's circle, in most of those cases, if not all, you had stresses with opposite signs. So the implication, or the important thing about that, is that if you have the principal stresses with opposite signs, then yielding will occur at a principal stress value less than the yield stress. Okay, so we've plotted over here a graphical representation of the Tresca yield criteria, or the maximum shear stress theory. So if your principal stresses are inside here, then you haven't yielded yet. If you're outside here, then you've yielded. If you're on the boundary, then you're at the point of yield. So if we take the case where you have the normal stress, the principal stresses have opposite signs. So let's say normal stress, the principal stress in the one direction is positive, and the minimum principal stress is negative, then you're down in here. Okay, so if you load it up, you move out along this way, and you get to this point here, which is the point at which the criterion says that you've reached yield. But look, the principal stress is less than the yield stress. All right, so you need to be making use of this failure criteria. You can't just work out what the maximum principal stress is and compare that with the yield stress. You have to look at the total state of stress. Okay, let's move on. So the next yield criteria is the maximum distortion energy theory, or the von Mises yield criterion. And this says that the structural component is safe, or that point of the component is safe, as long as the distortion energy per unit volume is less than that occurring in a tensile test specimen at yield. So this is similar to what we looked at with the maximum shear criteria. So we look at what's happening in a tensile test specimen at yield, how much distortion energy is there, or in other words, how much shear strain is there. Okay, so remember in last week's lecture I said that shear strain is change in shape or distortion. Okay, so this is still looking at shear deformation. Okay, all right, so I'm not going to go through the derivation of this equation, but we get down to an equation that looks like this. So the maximum distortion energy criteria says if you calculate the principal stresses, stress 1 and stress 2, do this calculation here. If that's less than the yield stress squared, then it hasn't yielded yet. Okay, at the boundary, if this expression on the left here is equal to the yield stress squared, then you're at the point of yield of that material. And we also can take this left-hand side here, take the square root of that, and we call that the von Mises stress. So this is an important thing to know. So if you have done any finite element analysis, and you will do it in Mech Design 2, usually the default output for your stress calculation or your stress analysis in the finite element method is the von Mises stress. Okay, so what the von Mises stress does is to take the complex state of stress, So for example, you've got stress in the X, normal stress in the Y, and shear stress X and Y. It takes that complex state of stress and converts it into a single scalar value that you can compare with the yield stress. Okay. So this is just a representation of the two criteria. So the maximum shear stress here criteria, and then the maximum distortion energy criterion. And you can see that the maximum shear stress criterion is more conservative. Okay, so it will predict yield before the maximum distortion energy does. So for example, if we have a loaded component, we calculate the stress and we get to a point here. As we increase our loading, we hit the boundary of the maximum shear stress criteria first. Okay, so that says as we load it up, we get to here, maximum shear stress criteria says we've reached yield. Whereas the maximum distortion energy says we've still got a little bit to go. Okay, so back to JC's notes. So again, this is just showing you what in a bit more detail what I just explained on the previous slide. It's also indicated here the case of pure shear, where you just have a torsion. And at this point, when the maximum principal stress is equal to the yield stress on 2, you get yielding, okay, which goes back to the definition of the maximum shear criteria. Yep. And if we look at the von Mises, or the maximum distortion energy criteria, at this point here, right, in pure torsion, we get to yield when the principal stress is equal to the yield stress divided by √3. Also, the maximum distortion energy theory represents experimental data more accurately as well. Okay, just quickly go through the fracture criteria for brittle materials. As I said earlier in the lecture, these are okay for very rough calculations, but if you want to do serious design for brittle materials to avoid fracture, you would look at linear elastic fracture mechanics. Okay. Yeah, so we looked at this before. If you have something in tension that's a brittle material, it will fail along the plane of maximum normal stress. Over here we've got the case of torsion. So we have pure shear, but even though we have pure shear in this orientation, we still have normal stresses at other orientations. So if you remember from Moore's circle, right, this is our stress element. If we plot that, right, those stresses, that stress there is shear only. So up here, 0 normal stress. Okay, and if we complete Moore's circle, then down here we have our principal stresses. So this one positive, and this one here negative. Okay, so if we twist in torsion a brittle material, you should see these failures at 45 degrees. So what I'm going to do here, usually in class, I do a simple demonstration with a piece of chalk. Now this is my only piece of chalk. I haven't had a practice run. So we'll see what happens here. So I'm going to twist this. Okay. So that worked all right. So I think you can see there that that failure surface is at roughly 45 degrees. Okay. All right. Okay, so the criteria. So the simple one, maximum normal stress theory for brittle materials, simply says calculate the principal stresses. If they're less than the ultimate tensile strength, then you're safe. If you're greater than the ultimate tensile strength, then you predict failure. Okay, so this is the case for if the ultimate tensile strength is the same in both tension and compression. For materials that have different values of the ultimate tensile strength in tension and compression, and many materials do, then you need to modify that criteria, and that's the Moore's criterion. Okay, so here in tension, typically the ultimate tensile stress in tension is less than it is in compression. Right? So we've just got this different shaped hexagon. The actual failure surface where you have principal stresses of opposite sign, you have this curved relationship, but we simplify this to straight lines. Okay, that's probably all I want to talk about for this. You know, we don't often use this very much. Again, it's good for quick calculations, and this is pretty much what you did in mechanics of solids, where you just calculated the principal stress, compared it with the ultimate tensile strength, and thought that was okay. Sometimes it is, sometimes it isn't. If you're down here, right, again, where you've got principal stresses are of opposite sign, then you're going to fail well before the principal stress gets to the ultimate tensile strength. So you need to be careful about that. Okay, so finally, factor of safety, or the design factor, is just a measure of the relative strength or safety of the component. So we're just comparing our ultimate or failure stress with an allowable stress. Okay, and failure could be yield, could be ultimate tensile strength, or it could be some other value. In later topics, we'll look at fatigue as well. Okay, so we'll look at the endurance strength when we calculate our factor of safety. When you're considering factor of safety, there's a whole bunch of different considerations to take into account, and you need to consider all of these when trying to work out an appropriate factor of safety. Typically, design textbooks will go through these in more detail, where in this particular subject, not going to go through all that. But we're now going to have a look at a worked example, and again, the solutions are just come up in the PowerPoint. So again, I encourage you to try and have a go at the problem on your own first, and then come back and try and follow along after you get stuck or you're not sure what to do. Okay, so we've got a problem here, typical stress analysis problem that we looked at in the first week or two, where you've got a loaded component. We've got a point somewhere in the component that we want to know the stresses at. Calculated the, so we've done the part of the work for you in this one and said at this point, these are our stresses. So we've got a normal stress in one direction and a shear stress, and we're asked to determine if these loads cause the shaft to fail or to yield, in this case, according to the maximum shear stress theory and the maximum distortion energy theory. Okay, so you've got an answer there that we're going to work to. Okay, so stress state, we can calculate from these stress analysis formula that we've seen before. And the principal stresses can be attained from Moore circle. Again, we're going to skip through this quickly just to keep the video short, but you can have a go at doing that for yourself separately and compare your results with what we've got here. So we've got our principal stresses, so we can see we've got a normal maximum principal stress of 95.6 positive, and our other principal stress minus 287. So using the maximum shear stress theory, so we've got opposite signs. So we use this version of the equation. So stress 1 minus stress 2 is this less than the yield stress to determine whether yield has occurred or not. So let's put those numbers in that we just calculated. Stress 1, 95.6 minus 286. and that comes out to be 382.2, which is greater than the yield stress. So the maximum shear stress theory predicts that yielding has just occurred. Right? Again, note that both of these principal stresses are way less than the yield stress. Yeah. So even though both principal stresses less than the yield stress, we've still predicted that yielding has occurred. All right, so let's apply the maximum distortion energy theory. Okay, so the equation here, this is the expression that we had from before. So if this is less than the yield stress squared, then we predict that yielding hasn't occurred. So let's put our values in again. Is this less than 360 squared? So 360 squared is 129,600. This is a little bit less than that. So according to the maximum distortion energy theory, this predicts that yielding has not yet occurred, but not by very much. All right, so we wouldn't be designing something to be just here, and also with experimental variation and statistical scatter, you could do 5 different components. Maybe 2 of them would have yielded and 3 haven't. Yeah. Okay. So, all right, and also this shows you the fact that the maximum shear stress theory is more conservative than the maximum distortion energy theory, right? Because this has predicted that yield has occurred, whereas this hasn't. Okay, another example. This time we've just gone straight to the stress element with our stresses, and we want to know what is the factor of safety at this point in the structure with these stresses using the 2 failure criterion again. Right, again, we've got an answer here, so you can have a go at working through the problem yourself first. So let's go. So first thing to do is construct Moore's circle. So from our stresses, we can calculate the average and the maximum shear stress. And then from that, we can get our principal stresses. So in this case, we have 85 as our maximum principal stress and minus 45 as our minimum. So applying the maximum shear stress criterion. So here, the yield stress was 250. So the corresponding shear stress at yield is half that, as we saw before, so 125 megapascals. Our factor of safety is the yield stress over the maximum shear stress that we have in our material. Okay, so let's just check here, right, whether we've got the absolute maximum shear stress. So what would be the stress in the Z direction? So if we go back to our, right, so we've got a plane stress case, so 0 stress in the Z direction. So where will our other 2 Moore's circles be? Right, plot one here. So stress Z is 0, so we'll have one here and the other one will be here. So in this case, the in-plane maximum shear stress is the absolute maximum shear stress. So this is okay. And if we plot that, plot that on the graphical representation of the 2 failure criteria, we can see that we're down in here, so well safe. Using the maximum distortion energy criteria, so here JC's just included the factor of safety into the criteria formula. So if we do input those values and we solve for the factor of safety, we get a factor of safety of 2.19. Okay. Alternatively, if we use the von Mises stress, okay, so remember I said this is important to understand for if you go to use finite element analysis, because usually the default output is the von Mises stress. Okay, so we can calculate that von Mises stress as the square root of this left-hand side of this equality here. And we'll see that that value is 114.3. And if we do the factor of safety is the yield stress or the failure stress divided by the stress that we've got from our design loads, we get the same as we've got over here, so a factor of safety of 2.19. Okay, so just in summary, here's where we are on this graphical representation of the failure criteria. So we had a maximum principal stress of 85 and a minimum principal stress of minus 45, so we're down here. If we increased the loading proportionally so that we move out along here, we get to this point here, which will be the point at which we predict yielding according to shear, and increase the loading a bit more, and we get to the point here where we predict yield according to the maximum distortion energy or the von Mises theory. And if you look at the ratio of this length here, so point T over 0 to H, that's our factor of safety in for the shear criteria, maximum shear criteria, and the ratio of the length from O to M over OH will be the factor of safety according to the von Mises criteria. We would never actually do this, like draw this and measure and do these ratios in practice. It's just a graphical indication of what's going on here. All right, so that's the end of the lecture. Again, oops, this was a little bit long, 37, sorry about that. Okay, so hopefully that was useful and somewhat interesting, looking at failure criteria and how we apply our stress analysis to strength-based design. And in the tutorials, you'll see some more examples of how to apply this. All right, so that's it for this week. I might see you next week. We'll see how we go, whether I do the lecture or JC does it. But have a good weekend. Stay safe, look after each other, and look after yourselves. All right, bye for now.